In this lesson we're going to look at the class of organic molecules called the alcohols, and we will begin by examining their physical properties. So here we have the alcohol ethanol with 2 carbons and the alcohol group at the end of the molecule. Now the alcohol group here carries a dipole. The oxygen is a far more electronegative atom than the hydrogen. So the OH bond here is highly polar, with the bonding electrons pulled across towards the oxygen atom. Because oxygen, located towards the top right of the periodic table, lots of protons in its nucleus which pulls these bonding electrons towards it. So if we look at another ethanol molecule, what happens here is we have an interaction between these alcohol groups, which is a strong interaction called a hydrogen bond. So whereas before in, for example, halogenoalkanes we had dipole-dipole interactions, again we've got a sort of a dipole-dipole interaction here, but it's a much stronger interaction than we would have in halogeno molecules. The reason for that is that this OH bond, because a lot of oxygen is particularly electronegative, it really pulls the electrons in this covalent bond strongly towards it. It has a very significant dipole here, and so you get what we call a hydrogen bond existing between the partially positive hydrogen on the alcohol group of one molecule and what we call a lone pair of electrons. So this is a non-bonding pair of electrons in the outer shell of the oxygen atom, which can form an attraction. This negative pair of electrons forms an attraction to the partially positive hydrogen on another alcohol molecule. And this is what we call a hydrogen bonding. Hydrogen bonding is somewhat stronger than the dipole-dipole forces we saw in halogenoalkanes, and is significantly stronger than the van der Waals forces that we see in alkanes and alkenes. And what that means is that these alcohol molecules are going to have much higher boiling points than alcohols or alkenes or even halogenoalkanes of similar chain lengths. And what we will see therefore is the alcohols, they've got higher boiling points. All of these will tend to be liquids instead of gases at room temperature. So for example, ethanol is a liquid, whereas ethane or ethene would be a gas. What we also find is that as well as having higher boiling points, the alcohols, certainly the short chain alcohols, are very soluble in water. They mix well with water. They dissolve in water, got a high solubility. Why is that? Well, because water also form these hydrogen bonds between the molecules. So if we draw out some water molecules here, we draw out a couple of water molecules. What we have existing between these water molecules is again hydrogen bonds acting between them. Now those hydrogen bonds are the strongest intermolecular force. This is the strongest type of force that exists between different molecules. Molecules such as alkanes and alkenes do not form a strong enough bond with water to interrupt these hydrogen bonds. Water molecules would much rather form interactions with other water molecules than they would with alkanes or alkenes or even halogenoalkanes, and so those molecules tend not to be soluble. But a molecule such as ethanol can form just as good a hydrogen bond with a water molecule as another water molecule can. So the ethanol molecules can interrupt these hydrogen bonds, and they can move in between the water molecules, and they can form hydrogen bonds between them. So if I draw an ethanol molecule here, this ethanol molecule can form a hydrogen bond here, again between the lone pair of electrons and this partially negative oxygen here, forms an attraction to the partially positive hydrogen atom on this water molecule. So these ethanol molecules will mix very well. So certainly you'll tend to find that the smaller alcohols, the shorter chain length alcohols, will be very soluble in water. As chain length increases, the alcohols become somewhat less soluble. So if I've got a very long chain alcohol here, I'm not drawing all the hydrogens, but you get the idea, these are all hydrogen atoms here. because as you get these longer chain alcohol molecules, the alcohol group now represents a smaller portion of the overall molecule. Most of this molecule is just a hydrocarbon chain here, which is obviously non-polar and doesn't interact with water molecules. So as the chain length gets longer and the alcohol group represents a smaller portion of this molecule, solubility will decrease as the chain length gets longer. The most soluble alcohols are the short chain ones. Solubility will decrease as the chain length gets longer, but certainly alcohol molecules are much more soluble than alkane or alkene or even halogenoalkane molecules of similar chain lengths, and certainly as well they will have higher boiling points. The first reaction of alcohols that we're going to look at is the reaction with halide ions. So for example, HBr here, aqueous HBr, will give us bromide ions, and we can react that with an alcohol such as ethanol in this example. Now the reaction conditions we will need here is a concentrated acid catalyst, and we will need to reflux the reaction mixture. So this is where we basically boil the reaction mixture and we keep then fit a condenser and we keep boiling and then condensing the vapor as it evaporates back to a liquid, and do that over and over again. And if we do that, what will occur is a nucleophilic substitution reaction, basically, where the bromide ions, Br minus, from the HBr will substitute the hydroxide group of the alcohol. And what we will produce is a halogenoalkane, in this case bromoethane, and we will also produce water, H2O. So just as we've seen, if we take a halogenoalkane, in the previous lesson we take a halogenoalkane, we can actually react it with hydroxide ions and replace the bromide with an OH to form an alcohol. We can also do the reverse, basically taking an alcohol with bromide ions and form a halogenoalkane. This reaction will also work with HCl or hydrogen iodide, and you can form a chloroalkane here or even an iodoalkane. The second reaction of alcohols that we're going to look at is what we call a dehydration reaction. Now, in a dehydration reaction, what we're going to do is we're going to eliminate a water molecule, basically, and by doing that we're going to form a double bond. So if we start off with ethanol, again here, what we can basically do is eliminate an OH group and a hydrogen, form water, and in doing that we'll form a double bond between these carbons. Now to do that, the reaction conditions, we're going to need to heat the reaction mixture, probably to about 170 degrees Celsius, and we're going to need to use a concentrated acid catalyst. Again, concentrated sulfuric acid, for example. And if we do that, what we will produce is an alkene molecule and a water molecule. And there we are. Now, a key reaction of the alcohols is oxidation. Now, when an oxidation of an alcohol occurs, the product will depend on what type of alcohol you've got. So what we're going to do is we're going to start with ethanol as an example. Now, ethanol is an example of what we call a primary alcohol. Now, basically a primary alcohol is when the OH group, the alcohol group, is connected right at the end of the carbon chain. So the carbon that the OH group is connected to is only connected to one other carbon here on its left, and that's called a primary alcohol. Now what we can do is we can oxidize that. Basically we oxidize it, we're adding an oxygen. So that O in brackets indicates an oxygen that is being provided by an oxidizing agent. And in a common oxidizing agent that we often use for this reaction is called potassium dichromate. And we need to acidify that. So H plus ions come from an acid, and we have potassium dichromate. It's basically an oxidizing agent that provides these oxygen atoms. Now, what will happen then, the first thing we will form here is an aldehyde. So what we actually form is ethanal. And we get that molecule, and we also get water produced. Make sure we balance the equation. 3, 4, 5, 6 hydrogens there, 3, 4, 5, 6, 2 oxygens here, 1 there, and 1 from the oxidizing agent. So there we form an aldehyde. The thing is, aldehydes are also very easily oxidized. So if you wanted to form the aldehyde, what you would have to do is you heat this reaction mixture, you would have to distill off the product here as soon as it's formed. Because otherwise, if you just carry on refluxing the reaction mixture, the aldehyde reacts further with the oxidizing agent. So here we have our aldehyde. And what will happen is it'll take another oxygen from the oxidizing agent, H plus acidified potassium dichromate, and what you will form is a carboxylic acid, COOH, and that's if you just continue to reflux the reaction mixture. So if you want to form an aldehyde by oxidation of an alcohol, you can, but basically as soon as you form the aldehyde, you'll need to distill that off from the reaction mixture and collect it, because otherwise, if you carry on refluxing the reaction mixture, that aldehyde will very quickly be oxidized on, and it will form carboxylic acid here, as we can see, ethanoic acid in this particular example that we see here. Now, what we have in this example here is propan-2-ol. Now, propan-2-ol is an example of a secondary alcohol. So why is this a secondary alcohol where ethanol was a primary alcohol? Well, the reason here, we can see the OH that we've, or the carbon that we've attached the OH to, is connected to 2 of the carbons. So whereas if we contrast that with ethanol, which we had earlier, so remember ethanol was this molecule. In this case, the carbon that we connected the OH to, that's this carbon here, was only connected to 1 other carbon, whereas in this case, the carbon that we've got the OH connected to is connected to 2 other carbons. So this is a secondary carbon, a secondary alcohol, whereas this was a primary alcohol. Now this time, we can carry out the same reaction. So the oxygen provided by an oxidizing agent, I'm going to use acidified potassium dichromate again. Yeah, acidified potassium dichromate goes from orange to green when it causes oxidization. So you'll know if this reaction is occurring, so you'll get a color change from orange to green. And this time, when you oxidize this, again you'll produce a water molecule. Again you'll get the carbonyl group, carbon double bond to O. But obviously this time, because it's a carbon, it's sort of in the middle of the molecule, we've got a ketone and not an aldehyde. We will again get water produced. Now, whereas before with the ethanol, we saw when we oxidized that, we got an aldehyde, and then that was oxidized very rapidly onwards to a carboxylic acid. The ketone cannot be oxidized any further. That's as far as it goes. So if you just reflux this reaction mixture for a secondary alcohol, your product, instead of being a carboxylic acid, will actually be a ketone, and that reaction will go no further. We've got a third example here of oxidation of alcohols, this time using methyl propan-2-ol. Now this is an example of a tertiary alcohol, because this time if we look at the carbon that the OH group is located on, this carbon is not just attached to 1, it's not just attached to 2 of the carbons, it's actually attached to 3. 1, 2, 3 of the carbons. So 3, tertiary means 3. This is a tertiary alcohol. Now when we try and oxidize this one, no reaction will occur. Potassium dichromate will stay orange, it won't go green, it won't be able to oxidize this alcohol. Really the reason for that is that carbon can only form 4 bonds. So if we wanted to form a double bond between the carbon and the oxygen, we'd have to break one of these other carbon-carbon bonds, and essentially that just takes too much energy, you can't break that. The other ones, we only had to break a carbon-hydrogen bond, we were able to do that. We can't break one of these bonds. A tertiary alcohol cannot be oxidized, whereas a primary alcohol could be oxidized to an aldehyde and then onwards to a carboxylic acid, Secondary alcohol could be oxidized to a ketone, but a tertiary alcohol cannot be oxidized at all. The final example of reaction of alcohols that we're going to look at is simply combustion. So basically combustion, what you're doing is you're heating the alcohol in oxygen and it burns. And alcohols burn with a very clean, smokeless flame. And they do that to produce carbon dioxide and water. So alcohols actually can make quite good, very good in fact, fuels. So if we balance this equation, we've got 2 carbons there. So we're going to need 2 CO2s here. So we've got 2 carbons on this side. We've got 1, 2, 3, 4, 5, 6 hydrogens here. So we're going to need 3 H2Os, because 3 H2s make 6 hydrogens here. If we look now overall, we've got 2 times 2, that's 4 oxygens here. 3 more, that's 7 oxygens. We've got 1 oxygen there. So we're going to need 3 O2s on this side. 3 2s make 6, 1 is 7. And that matches the 7 oxygens on the right-hand side here. So there we've got a balanced equation for the combustion of ethanol. Okay, that's for ethanol, but whether you've got methanol or propan-1-ol, propan-2-ol, butan-1-ol, they'll all burn very nicely in oxygen to produce carbon dioxide and water. Some countries, such as Brazil, where you can easily grow sugar, and you can therefore produce ethanol fairly cheaply by fermentation. So in those countries, they're going to use things like ethanol as a fuel quite commonly.